Let us now study the armature reaction. So this armature reaction takes place in both AC and DC machines. Here we will study the armature reaction in DC machines. Now you know that in case of a DC machine there are field poles, and when field winding is excited means when field winding is connected to a DC supply, then the main flux is produced by the field poles. Now if the machine is not loaded, that means if the machine is operating under no load condition, then the current in armature conductors is equal to 0. So in case of unloaded machine, there is no current in the armature conductors. However, when the machine is loaded, current flows through armature winding also. And therefore, this armature current produces its own flux. And that's why in the machine there are two fluxes: the main flux, which is produced by field poles, and the armature flux produced by the armature current, which is flowing in the armature winding. So under actual load condition, main flux as well as armature flux exist simultaneously, and therefore there is an effect of armature flux on main flux, and this is called as armature reaction. So armature reaction is defined as the effect of armature flux on main flux. If the machine is not loaded, then armature current is 0 and armature flux is also equal to 0. Then there will not be any armature reaction. But when the machine is loaded, there are two fluxes: main flux and armature flux. And the effect of armature flux on main flux, it is called as armature reaction. Let us now see the main flux distribution if the current in armature conductors is 0. Now here a two-pole machine is shown. One pole is north and second is south. Now in this case it is assumed that current in armature conductors is equal to 0 as the machine is not loaded. So at under no load condition, current flowing through these armature conductors is equal to 0. Now here the line joining the centers of north pole and south pole, it is called as polar axis. So this axis we call it as polar axis, whereas the axis which is perpendicular to this, so this axis, it is called as interpolar axis, and this axis, it is the polar axis. Now when the winding is excited, means when field winding carries current, then north and south poles are produced and magnetic field is set up between north and south poles, and the direction of magnetic lines of force, it is from north pole to south pole. Now in this case, this axis, it is called as MNA, that is magnetic neutral axis. So magnetic neutral axis means along this axis no EMF is produced in armature conductors. For example, if in this position, if there is one armature conductor, then its movement will be parallel to the main flux. So it will not cut any flux, and therefore EMF induced in that conductor will be equal to 0. Similarly, if there is one conductor here, then its movement will be parallel to the magnetic flux, and therefore no EMF will be induced in that conductor. So the axis along which no EMF is induced in the armature conductor, it is known as magnetic neutral axis or MNA. Now MNA can be also defined as the axis which is perpendicular to the flux passing through the armature. So this is the flux passing through the armature, and the axis which is perpendicular to the flux passing through the armature. This axis, it is magnetic neutral axis. Now in this particular case, means when armature current is 0, you can see that geometric neutral axis coincides with the magnetic neutral axis. So geometric neutral axis or GNA, it coincides with MNA, that is magnetic neutral axis. Now, if there is no current in the armature conductors, means here current flowing through armature, if it is 0, then the flux is distributed symmetrically with respect to the polar axis. So this is the polar axis, and with respect to this polar axis, distribution of main flux, it is similar. And second thing is, if there is no current in armature conductors, the magnetic neutral axis coincides with the geometrical neutral axis. So MNA coincides with GNA, and the main flux is symmetrical with respect to the polar axis if there is no current in the armature conductors. Now here you should note that brushes are always placed along MNA. So brushes are always placed along magnetic neutral axis. And that's why MNA is also called as axis of commutation. So we have studied commutation already. So whenever a conductor passes from north pole to south pole, there is reversal of current. Or similarly, whenever conductor passes from south pole to north pole, again there is a reversal of current. And this reversal of current takes place along this magnetic neutral axis. And that's why this axis, it is called as axis of commutation. Now here, this main flux, it is symmetrical with respect to this polar axis, and therefore the magnetomotive force producing the main flux can be represented by vector OFM. So this is vector OFM, and it is parallel to this polar axis, or it is perpendicular to this magnetic neutral axis. Now let us consider a case when there is no excitation of field windings. Means current through field winding is 0, but current is flowing in the armature winding. Means now let us consider a case when the field winding is unexcited and the armature conductors are carrying current. Now the direction of current can be determined by applying Fleming's right hand rule. So here the rotation is in clockwise direction. The flux is from north pole to south pole. So if you apply Fleming's right hand rule here, then you can see that the current in the conductors under north pole, this current will be inward, whereas for these conductors which are under the influence of south pole, these currents will be outward. So the current in the conductors under N pole, these are shown by cross, and current in the conductors under south pole, these are shown by a dot, because the inward current or downward current is represented by crosses, and outward or upward current is represented by dots. So here the current is inward and here the current is outward. Now we know the magnetic effect of electric current. Means whenever current flows through a conductor, magnetic field is produced. And the direction of magnetic lines of force can be found by applying corkscrew rule or right hand grip rule. So what is right hand grip rule? We have to grip the conductor in our right hand such that thumb is in the direction of current. Then the other fingers, they will indicate the direction of flux. So here the current is inward, and therefore for these conductors the magnetic flux will be in clockwise direction. Whereas for these conductors the magnetic field will be in anticlockwise direction. So when current flows through armature conductors, sorry, magnetic field will be set up, and this magnetic field is clockwise for the conductors under north pole, and it is in anticlockwise direction for the conductors under south pole. Now here you can see that this flux is symmetrical with respect to this magnetic neutral axis, and therefore the resultant MMF produced by this armature current. So this resultant MMF is downward, and it can be represented by vector OFA. Now vector OFA is parallel to the brush axis or magnetic neutral axis. Now in this case, this OFA, it is parallel to the MNA or magnetic neutral axis, or it is also called as axis of commutation. Now here you have to note that the magnitude of armature MMF, that is OFA, it depends on the magnitude of armature current. If more current flows through armature conductors, then the magnitude of OFA will be more. So the magnitude of armature current, as it is increases, the armature MMF will also increase. Means this armature MMF, it depends on load on the machine. So as the machine is loaded or as the load is increased, this armature flux will also increase. So now we have seen that if there is no current in armature, this is the flux distribution of main flux, and it is symmetrical about the polar axis. If there is no current in the field winding and there is only current in the armature, this is the flux distribution because of armature current, and this main flux can be represented by OFM and armature flux can be represented by OFA. In fact, not flux, the magnetomotive force. So magnetomotive force required to produce the main flux, that is OFM, and magnetomotive force because of armature current, that is OFA. Now in case of a machine, both these flux will exist simultaneously. Means when the machine is working, there will be main flux as well as armature flux, and therefore there will be effect of armature flux on main flux, which we call it as armature reaction. Now you can see that in this region the main flux and armature flux both are in the same direction, whereas in this region, main flux and armature flux, these are in opposite direction. Similarly, here the main flux and armature flux are in opposite direction, whereas in this region the main flux and armature flux, they are in same direction. So in these two areas there is crowding of flux or strengthening of flux. So this tip, it is called as leading pole tip. Similarly, this tip, it is leading pole tip, and at this leading pole tip there is strengthening of flux or crowding of flux, and these two pole tips are called as trailing pole tips. So at trailing pole tips there is weakening of flux. So here the field will become weak, and here the field will become strong. So the effect of armature reaction is, in one half part of the pole the flux will become strong, and in the other half part of the pole the flux will become weak. So the flux will be distorted, and now it will not be parallel to the polar axis, whereas it is now inclined as shown here, and that's why the magnetic neutral axis will change. Now if there is no current in armature conductor, or if there is no current in field winding, then geometric neutral axis and magnetic neutral axis both coincide each other. But because of armature reaction, this magnetic neutral axis will get shifted by certain angle. That angle is called as theta. So through certain angle theta, the magnetic neutral axis gets shifted, and therefore we have to change the position of brushes also, because brushes are placed always along with the magnetic neutral axis. So here this vector represents OFM, that is the main flux, and this vector represents OFA, that is armature flux, and in the air gap both fluxes are there simultaneously, that is OFM as well as OFA, and therefore resultant flux in the air gap will be the sum of OFM and OFA, and therefore this is the resultant flux. So resultant flux will be FR, which is the sum of the main flux and armature flux. So here what happens? There is distortion of flux. Now if we consider the armature flux only, now because of shifting of magnetic neutral axis, we have to shift the position of brushes also. So now there is rearrangement of armature conductors. So some conductors, for example this conductor, previously it was under the influence of south pole, but now it is under the influence of north pole. And some conductors, for example this conductor, previously it was under the influence of north pole, now it is under the influence of south pole. So this current, for this current, the direction of current, it was previously outward, but now it is inward. And for this conductor, previously the direction of current, it was inward, but now it is outward, and therefore this armature flux is now symmetrical about the new magnetic neutral axis, and therefore the armature flux, it can be represented by this vector OFA. So the armature MMF is now represented by OFA, and this vector is not vertical but it is inclined by an angle theta. So this angle theta and this vector OFA, previously it was vertical, but now it is inclined with certain angle theta, through which the magnetic neutral axis is shifted. So now the OFA can be resolved into two rectangular components. One is OFD. So this OFD is parallel to the main flux, but it is opposite to the main flux. And second component is OFC. So this OFC, it is perpendicular to the main flux, or it is perpendicular to the polar axis. So armature flux or armature MMF, now it can be resolved into two components, OFD, which is parallel to the polar axis but it is opposite to the main flux, and OFC, it is perpendicular to the polar axis. So the component OFC, it is perpendicular to the main flux, that is OFM, and therefore this component OFC, it produces distortion of the main field, and now the main flux gets distorted, and therefore this component OFC, it is called as the cross magnetizing component of the armature reaction. So this OFC, it produces distortion of main flux, and it is called as cross magnetizing component of armature reaction. And the other component is OFD. It is in direct opposition to OFM. OFM is the main flux MMF. So main flux MMF, OFM and OFD are in direct opposition, and therefore OFD causes demagnetization or reduction of the main flux. So main flux is reduced because of this component OFD, and therefore this OFD is called as demagnetizing component of the armature reaction. So there are two components of armature reaction, OFD and OFC. OFC is called as cross magnetizing component and OFD is called as demagnetizing component. So to summarize the armature reaction, there are two effects. One is it demagnetizes or weakens the main flux. The main flux will reduce because of the armature reaction. And second is it cross magnetizes or distorts the main flux. So main flux gets distorted because of the armature reaction. Now because of first effect, that is because of demagnetizing effect, what happens? Flux is reduced and therefore generated voltage is also reduced because of demagnetization effect. And because of the second effect, the magnetic neutral axis gets shifted, and because of shifting of MNA, commutation will not be proper, and therefore there will be sparking at the brushes. And here one important point you should note that this both distorting as well as demagnetizing effects, these are dependent on the amount of load. So if there is increase in load, there is increase in armature current. Then there is increase in the effect of armature reaction. And because of that, both these distorting and demagnetizing effects will increase with increase in the armature current, that is with increase in load. In our next video, we will see how to calculate demagnetizing and cross magnetizing ampere turns, and we will also solve few numerical problems on calculation of these ampere turns. Thank you. Stay home, stay safe.